Let's consider the next chapter, that is on thermionic emission and radioactivity. What exactly is thermionic emission? This particular branch of physics deals with modern solid-state physics and also has semiconductor devices in it. Talking about thermionic emission, we say that it is the spontaneous emission of charged particles from an electron-rich cathode plate when it is heated electrically and indirectly is called as thermionic emission. Why do we use this thermionic emission on day-to-day basis? We use thermionic emission as in the case of a television. The picture tube of the television is made up of the hot cathode ray tube, which works on the principle of thermionic emission. Students are fond of playing computer games. The monitor of the PC is basically made up of the hot cathode ray tube. So also we see in the hospitals that the heart signal beats are being converted into the visual signals, which also constitutes the hot cathode ray tube. Talking about thermionic emission, we have certain terms which we learn in this chapter. Though there are no prerequisites for this particular chapter, because this being entirely a new solid-state physics, we still have to remember while starting this chapter that this is something to do with your binding energy, something to do with threshold energy, something to do with work function, something to do with thermionic emission. So the most important terms that are used in this particular chapter are going to be thermionic emission, work function, threshold energy, and binding energy. Along with this, we should also remember in the second half what radioactivity deals with. It is a nuclear phenomena and no chemical changes would affect radioactivity. Talking about the concepts that are related in this particular chapter. First, we define what is binding energy. The energy that binds the electron to the nucleus on account of electrostatic force of attraction is called as binding energy. The electron, while moving around the nucleus, we see that it is bound to the nucleus. Why? Because the electron is negatively charged, the nucleus being positively charged. Definitely there is a force of attraction between the nucleus and the electron. So this force that binds the electron to the nucleus is called as the binding energy. It is measured in electron volts. The second term that we consider in this case is threshold energy. When we heat this particular substance, when we heat it electrically and indirectly, we see that the electron that is present in the outermost orbit is being emitted. So the minimum amount of energy required to remove the electron from its outermost orbit, thereby overcoming the binding energy, is called as threshold energy. Numerical value of threshold energy is always greater than binding energy. So how do we define threshold energy? Minimum amount of energy required to remove the electron from its outermost orbit, thereby overcoming the binding energy, is called threshold energy. It is also measured in electron volt. Third part is work function. It is true that certain amount of energy binds the electron to the nucleus. It is also true that on supply of thermal energy, the electron is removed from the outermost orbit. But in the process, certain amount of work is done. That work done is a function of the thermal energy that is provided, which is called as work function. Numerically, work function is equal to threshold energy. With these basics terms that we are using over here in thermionic emission, we go on to the application of thermionic emission, that is a hot cathode ray tube. I'll draw the figure over here while explaining the principal construction and working. The hot cathode ray tube works on the principle of thermionic emission. A hot cathode ray tube works on the principle of thermionic emission. It consists of a highly evacuated tube which is narrow at one end and broad at the other. It consists of a highly evacuated tube which is narrow at one end and broad at the other. Towards the narrow end lies a high resistance coiled coil which is connected to a low tension battery, a key and a rheostat. This high resistance coiled coil indirectly heats an electron rich cathode plate. This high resistance coiled coil indirectly heats an electron rich cathode plate. By the process of thermionic emission, thermions are liberated. The emission of thermions is not uniform. Hence, to regulate the flow of thermions, it is made to pass through a wire mesh called the control grid, which is maintained at a positive potential with respect to cathode. When these thermions sieve through the control grid, they do not possess enough kinetic energy to reach the screen. Hence, in order to impart them with large kinetic energies, they are made to pass through a solid circular cylinder called the accelerating anode, which is maintained at a high tension AC voltage with respect to the grid. This accelerating anode has a small annular hole in it. So because of this orifice, there is decrease in area of cross section and hence increase in velocity. As these thermions gush out of the accelerating anode, they move in all possible directions. In order to streamline them, they are made to pass through a deflecting system which consists of two pairs of plate. One, the vertical plate called the XX plates. Second, the horizontal plates called the YY plates. The vertical plates align the thermions in the horizontal direction, hence called the XX plates. The horizontal plates align the thermions in the vertical direction, hence called the YY plates. The combined effect of XX and YY plates results in a fine stream of thermions which goes and strikes the fluorescent screen, which is coated with barium platinocyanide or zinc blend, producing a bright spot. There is a graphite coating across the slant edges of the picture tube, purely so that the energy that is being set across is not being absorbed by the sides and the focus of the thermions are straight onto the fluorescent screen. Applications of cathode ray tube, as I said earlier also, is the television tube, PC monitor and electrocardiograph. This chapter has a second part in it, which is called as radioactivity. Now, what exactly is radioactivity, or how does radioactivity play a vital role? We see that radioactivity is occurring because of two basic reasons. One, because the atomic number of the substance is greater than 82, that is, its nuclei is heavy, which results in natural radioactivity. So elements such as radium, uranium, plutonium and so on, we see that because the atomic number is greater than 82, definitely it exhibits radioactivity. However, for substances or elements which have atomic number less than 82, also under certain circumstances exhibit radioactivity. The condition for such substances to exhibit radioactivity is the neutron-proton ratio, that is the constituents of the atom. If the number of neutrons exceeds the number of protons by a ratio of 1.5, then we say that the substance is radioactive. This substance being radioactive definitely disintegrates to give three types of basic radiations. The first radiation is alpha radiations, second beta radiations, and third gamma radiations. Talking about alpha radiations are the radiations that are equivalent to a helium atom that has been liberated. So, when a nuclear substance is taken and an alpha particle is emitted, we see that the atomic number reduces by 2 and atomic mass number reduces by 4. So, we see that an equivalent of helium atom is being liberated out. The equation here states the element X having atomic number Z, atomic mass number A, when liberates an alpha particle, we see that Z reduces by 2, becomes Z minus 2, A reduces by 4, becomes A minus 4. So we get a new element over there as Y, having atomic number Z minus 2 and atomic mass number A minus 4. Talking about beta emission, radiation form wherein we say it is equivalent to an electronic charge that is being liberated. So when an electronic charge is being liberated, the corresponding change in the element is that the atomic number increases by 1. So if I have a radioactive substance or an element as X, ZA, the atomic number and atomic mass number, and a beta particle is liberated, then we see that X turns to be Y, a new element, with atomic number Z increased by 1, Z plus 1, atomic mass number A remaining constant. So one electronic charge is being removed from that particular substance to give out the beta radiations. As far as gamma radiations are concerned, these are electromagnetic in nature, and these radiations definitely create or turn the excited state of an atom into a normal state of an atom. What exactly is an excited state of an atom? When we see that the electrons are getting filled across different orbits, they do so by applying a particular rule, the rule of 2n square. In this case, we see that the first orbit has got a maximum capacity of 2 electrons, the second 8, the third 18, the fourth 32, and so on. However, in actual, we see that the elements do not fill up the electrons as specified by this particular rule. Because if we consider an element having atomic number 19, that is potassium, we see that the electronic configuration is 2, 8, 8 and 1. That means the third orbit, if we just focus ourselves on the third orbit, we see that it has got a deficit of 10 electrons still to its maximum capacity. Then why is it that it goes on to the next orbit? That is the first electron that is left out in the outermost orbit. Why is it that it shifts to the last orbit? That is purely because the third orbit has completed its octet, attained its stability, and then shifted to the next orbit. However, because of this deficit, this one electron that is present in the outermost orbit has a tendency to jump into the lower orbit. When it jumps into the lower orbit, it acquires that particular energy, because orbit is nothing but it's an energy level. So as soon as an electron jumps from a higher orbit to a lower orbit, that means it has attained that particular energy, and at that particular state we see that it is excited or it is unstable, because then it picks up a configuration of 2, 8 and 9. Under this circumstances, we say that this particular atom is an excited atom. So this phase of excited does not remain for long. However, it redirects itself back onto the original orbit, that is the fourth orbit. Whatever excess amount of energy it has gathered while jumping into the lower orbit is released in the form of radiations, and these radiations are called as your gamma radiations. They are electromagnetic in nature. They are not affected by electric and magnetic fields. However, when alpha beta particles are emitted and we make them pass along an electric field, we see that the alpha particles are deviated towards the negative plate, proving that alpha particles or alpha radiations are positively charged. Similarly, the beta particles get deviated towards the positive plate purely because beta particles are negatively charged particles. So the deflection in the electric field and magnetic field clearly signifies the nature of alpha and beta particles. A common question that they normally put across is, if a radioactive substance is oxidized, what is the effect on radioactivity? Now, radioactivity is a nuclear phenomena. That means anything to do with the nucleus will definitely affect radioactivity. But since chemical oxidation, decomposition, or whatever chemical process is an orbital phenomena that is to do with the electrons and not the nucleus, we see that any change or any chemical changes do not affect radioactivity. So a clear conclusion over here is no chemical changes affect radioactivity because radioactivity is a nuclear phenomena. You have something what is known as carbon-14 dating also, C14 dating. What exactly is this dating process? When we say dating process, we mean to say that how do we determine the age of a specimen? I have a plant specimen. During its lifespan, we see that it is absorbing carbon dioxide and carbon monoxide from the atmosphere. During its lifespan, it absorbs these two gases with the isotopes of C12 and C14 present in it. So, after the specimen dies, we see that we bury this specimen inside the ground. When it is buried inside the ground, out of C12 and C14, we know that C14 is disintegrated because of NP ratio being greater than 1.5. When this C14 disintegrates, it starts liberating beta particles. When it starts liberating beta particles, after a certain interval of time, say after 10 years, 15 years, 20 years, a soil sample is picked. When this soil sample is picked, they test this particular sample in a counter or in an instrument which is called as a Geiger counter. This counter determines the particles that are present in it. These beta particles count will determine how long the specimen was buried in the ground, and definitely we bury a specimen only after it is dead. So we know the birth year, we know the death year. Depending on the birth year and the death year, we can definitely define the age of the specimen. That is how long the specimen survived or lived. We say this method is a very crude method purely because when we select a sample, we do not know the source of the sample. We can take a sample as deep as 100 feet. We can take a sample as far away as 100 feet. So the number of beta particles present across various depths and various lengths are going to differ. And when the number of beta particles are differing, definitely whatever we estimate, saying that this particular specimen was living or was there in so and so years, is inaccurate. So the accuracy of this experiment definitely is dependent on the accuracy of testing the beta particles near the specimen. In this, we consider a question something like this. Say, for example, when a beta particle is emitted, what is the relative change of this particle being emitted from an element? Where does the element shift, whether towards the right or towards the left in the periodic table? When we say that beta particle is emitted, we know that the atomic number increases by 1. And when the atomic number increases by 1, definitely this element would shift one place towards the right in the periodic table. Talking about another application-oriented question in this particular chapter, which physical parameters are conserved in a nuclear reaction? When a nuclear reaction takes place, which are the parameters that are basically conserved in it? First one, conservation of momentum. We studied in the first chapter what exactly is momentum. So in this particular reaction, in a nuclear reaction, definitely the momentum gets conserved. Second one, conservation of charge. Charge also is conserved in a nuclear reaction. Then conservation of nucleons. Nucleons are nothing but the particles, subatomic particles that are present in the nucleus of an atom. And the conservation of energy. Because we know that energy can neither be created nor be destroyed. So the physical parameters that are basically conserved in a nuclear reaction are, once again, conservation of momentum, conservation of charge, conservation of nucleons, and conservation of energy. Talking about another question, which are the three principles on which the operation of a cathode ray tube depends? The three principles on which the operation of a cathode ray tube depends are thermionic emission, that is emission from the cathode ray plate when we see that it has been heated electrically and indirectly. Second one, deflection of electron beam in electric and magnetic fields. This deflection is caused because of varying electric and magnetic fields that are set up across the vertical plates and the horizontal plates. Third one is fluorescence that is produced by the screen. We have a fluorescent material and the thermions strike it. As a result, we see that fluorescence is produced. So, three principles on which cathode ray tube operates are thermionic emission, deflection in electric and magnetic field, and fluorescence. This chapter, being more on a theoretical part, definitely involves least number of numericals. So definitely it's an easy version for you all to score on it. But then at the same time, you should know simple subtraction of 4, subtraction of 2 and addition of 1, because very simple examples involving these mathematical operations are put across as far as your boards are concerned. So make sure that you know addition of 1, you know subtraction of 2 and you know subtraction of 4, so that you can score maximum in whatever small numericals are put across. But basically this chapter is on a broad-based spectrum, a theoretical chapter. You've seen how interesting the chapter was. Definitely it showed how different nuclear reactions are taking place What is the use of these nuclear reactions? What is the use of thermionic emission? Why is it that we are studying the hot cathode ray tube? I mean, nobody could have really visualized also that this television that I'm watching in front of me is a hot cathode ray tube or is working on the principle of thermionic emission. Yeah, this is what we say is modern physics. The physics that is going to come across henceforth is going to be based on this particular concept. What is the weightage for this part as far as your boards are concerned? Or how much is the coverage of this as far as your boards are concerned? To be a very safer side, let's put it as around 14 marks in your boards. A clear-cut distinguishing factor in this part of the chapter is that section A has got 2 marks, section B has got around 12 marks. The entire question number 10 is based on nuclear physics radioactivity. This is the first question that you should choose in section B while choosing an option. 100% assured performance in this chapter could be taken up. Well, we've already studied this chapter. We've studied the concepts. We have studied how we apply thermionic emission on a day-to-day basis. So how do we recap this particular chapter, or how we can just revise it, in a short interval of time? Thermionic emission deals with three basic fundamental quantities. Binding energy. How do we define binding energy? The energy that binds the electron to the nucleus on account of electrostatic force of attraction is called as binding energy. Then we had the threshold energy. Threshold energy is nothing but the minimum amount of energy required to remove the electron from its outermost orbit, thereby overcoming the binding energy. And then was the work function. With work function, we had the work that was done in removing the electron from the outermost orbit is a function of the thermal energy provided. And this work function is numerically equal to threshold energy. Then we had the application to one of the most important principles of thermionic emission, that is hot cathode ray tube, wherein it was divided into three parts. The electron gun, responsible for emission of thermions, the deflecting system, which deflects the thermions so as to align them on the screen, and third one was the fluorescent screen, which produces fluorescence. We have the applications of hot cathode ray tube in form of a television TV tube monitor or PC monitor or an electrocardiograph. The second half of the chapter was radioactivity, which is a nuclear phenomena occurring on two accounts. One, because of the instability due to the heavy atomic mass of the nucleus. At the same time, because of the neutron-proton ratio exceeding 1.5. Divided into two categories: natural radioactivity, artificial radioactivity. Example for artificial radioactivity is carbon-14 dating. At the same time, radioactivity liberates or emits three types of emissions: alpha, beta, gamma. Alpha are positively charged, beta are negatively charged, gamma is neutral. Alpha is deflected towards the negative plate, proving that alpha is positively charged. Beta deflected towards the positive plate, proving that beta is negatively charged. And gamma goes undeviated, because gamma radiations are nothing but electromagnetic radiations and are not affected by electric and magnetic fields.